Very good morning, students. So today we will discuss about the simple harmonic motion equations and its solution. Okay. So in our previous lecture, we have discussed, okay, that what is oscillation, what is the basic introduction of the oscillation, what is the periodic and oscillatory motions. Okay. We have in a very detailed manner discussed about the period and frequency. Okay, also we have discussed about the displacement and the phase equations, periodic functions. Okay, so today we will talk about the basic of the simple harmonic motion equation and their solutions. So students, let us suppose or consider a particle of the mass small m that is executing the simple harmonic motion. And what is its path? Its path is XOS. XOX, as you can see in a diagram. See this. In this diagram, the main position of the particle is capital O. Okay. Now let the speed of the particle be V naught. And when it is at position P at a distance NO from O, then at t equal to 0, the particle at P, that is the moving towards the right. And at t equal to t, the particle is at Q at a distance x from O. See this in a diagram. So at t equal to 0, the particle at the P position, that is moving towards the right hand side. Now at t equal to t, see this in the next. The particle is at Q, see this, at a distance x from O to Q. So these are two positions of the particle we have defined at t equal to 0, that is at point P, and at t equal to t, that is at point Q. And its velocity, already I have told you that it is V. Okay. Now the restoring force F vector at capital Q, that is given by F vector equal to minus K into X vector. Here K is the positive constant. Now F vector equal to M into A vector. Here A vector is the acceleration at capital Q. So we can redefine that F equal to M into A, we all know. And also we have studied F equal to minus K into X vector. So if we equate both values, that is, if we equate MA vector equal to minus KX vector, then A vector becomes minus K upon M into X vector. Now what we will do? We will put the value K by M equal to omega square. Okay. We will put the value K by M equal to omega square. So A becomes minus omega square X. Okay. A becomes minus omega square X. And also by this assumption K by M equal to omega square, the value of omega becomes under root K by M. The value of omega becomes under root K upon M. So we can say that A vector will be equal to, that is minus K by M into X vector. We can also write it is minus omega square into X vector. And also we know that A vector defined by the two-time differentiation of the position vector, that is the d2x upon dt square. So we can also write that d2x vector upon dt square will be equal to minus omega square into x vector. Okay. So if we want to make a differential equation of this SHM, simple harmonic motion, then this equation becomes, because we know that d2x upon dt square becomes minus omega square into x vector. So it becomes d2x upon dt square plus omega square into x, that will be equal to 0. This is the differential equation for the linear simple harmonic motion. Okay, so what we have to see this again, that first we all know that the restoring force F vector, that is at point Q, it equal to F vector into minus K into X vector. And acceleration at point Q in this diagram, see this, that is F vector equal to M into A vector. So when we equate both equations, it becomes MA vector equal to minus K X vector. So A vector becomes minus K by M into X vector. And by putting the value k by m equal to omega square, omega becomes under root k upon m. So a vector becomes minus k by m into m vector. Okay. So it becomes minus omega square x, or a vector equal to d2x upon dt square. So that differential equation becomes d2x upon dt square plus omega square x equal to 0. That is the differential equation for the linear simple harmonic motion. Now let's talk about the solution of the differential equation. See this. The differential equation for the simple harmonic motion that has the following solutions. First, that x equal to capital A sin omega t. Okay. So this solution we will use when the particle is in its mean position at point O. As you can see in the figure A, see this. This is the particle mean position. And we will use x not equal to A sin phi, where we have replaced omega t to the term phi when the particle is at position and not at the mean position. When it is in the mean position, we use A sin omega t. And when the particle is not at the mean position, then we will use x not equal to A sin phi. Okay. So the equation x becomes A sin omega t plus phi when the particle at q in the figure at any time t. So there are three terms are there. First, when the particle in its mean position at the point O, then second, then particle is not at the mean position, and the third is when the particle is at q in the figure at the time small t. Okay, students. So we can say that these solutions can be verified by the substituting these x values in the above differential equations for the linear simple harmonic motion. What is our linear simple harmonic motion equation? That is d2x upon dt square plus omega square x equal to 0. By putting the value of x, a sin omega t or a sin phi or a sin omega t plus phi in this equation, we can verify the values for the linear simple harmonic motion. Okay. Now, student, let's talk about the angular simple harmonic motions. Okay. Now, what is the angular simple harmonic motion? That is a body free to rotate about an axis that can make angular oscillations. For example, you can say a photo frame or a calendar that is suspended from a nail on the wall. So if it is the slightly pushed from its mean position and released, then it makes the angular oscillations. Okay. So what should be the condition for angular oscillation? Now we will talk about all the conditions for the angular oscillation to be the angular SHM. See this. The body must experience a net torque, that is the restoring in nature, and if the angle of the oscillation is small, this restoring torque will be directly proportional to the angular displacement. That means T will be directly proportional to minus theta, or we can say T equal to minus k theta. And also we all know that the T also equal to I alpha. So we can say that alpha will be equal to minus k theta. Okay. T proportional to minus theta, T equal to minus k theta, T equal to I alpha, A becomes minus k theta. And we all know that alpha equal to d2 theta upon dt square. See, students, in the angular motion, we all know that we represent displacement by the term theta. In the linear displacement, we represent displacement by the term x. And in the angular displacement, we represent the term displacement by the theta. So this equation becomes I d2 theta upon dt square equal to minus k theta. Okay. So what this equation becomes, d2 theta upon dt square, it becomes minus k upon I into theta, or you can say k upon I, we can write the term omega square, and it becomes minus omega square into theta. Okay. So d2 theta upon dt square, that equal to minus omega square theta equal to 0. That is the differential equation of an angular simple harmonic motion. And solution of this equation is angular position of the particle with the respect to time. Okay. So we have seen till now the equations for the linear displacement as well as for the angular differential equations. Now theta equal to, we all know that theta equal to theta naught sine omega naught t plus theta. Here the angular frequency omega equal to theta naught omega naught cos omega naught t plus theta. Here theta naught is the amplitude of the angular simple harmonic motion. Okay, theta naught is amplitude of the angular SHM. Also we can say that by using this in the equation omega equal to theta naught omega naught cos omega naught t plus phi, we can use directly as the amplitude of the angular SHM. These are some examples of the angular SHM, like the simple pendulum, seconds pendulum, the physical pendulum, torsional pendulum. All the types of the pendulum is the example of the angular simple harmonic motion. Okay. Now let's do the qualitative analysis of the simple harmonic motion. So you can see there are 2 points are there. First is A, another is A dash, extreme point, and there is a mean position at point O. Now students, let us consider a particle that is executing the simple harmonic motion between A and A dash about the passing through the mean position or the equilibrium position. So we can do the analysis like this. See this. So students, there are 2 mean points first. So there are 1 mean point, 2 extreme points. So at the right hand side, there is x equal to A, and at the left hand side, there is x equal to minus A. The net force will be equal to 0 at the mean position. Okay. And the displacement is capital A and minus A. Okay. So see this. There is displacement, that is x equal to minus A. There are basically 2 types of displacement are there. You can see here minus A, at the mean there is 0, and at the top right hand side there is plus A. Now if we talk about acceleration, there is mod A will be equal to maximum at either side, left or right side. Always if we take a mod of the acceleration, it will be the maximum value, and at the mean position it will be 0. If we talk about speed, at both sides, at that mod will be 0, and it will be the maximum at the mean position. So students, just remember it, at the mean position the speed will be maximum, otherwise at the extreme points it will be 0. Now let's talk about the kinetic energy. Again, at the extreme points it will be 0, either it will be left side or right side, and at the mean position it will be the maximum value. Okay. Now let's talk about the potential energy. Again, there is the maximum potential energy at either side, extreme points, and it will be the minimum at the mean positions. Okay. So students, these are some few points which we should be remember, that kinetic energy will be 0 at the either side, but potential energy will be maximum. Kinetic energy will be maximum at the mean position, but potential energy will be minimum. Acceleration will be maximum on either side, but velocity will be 0. It will be the maximum velocity or speed, you can say, at the mean position. So students, these are some points which we should be remember about the mean position. So today we have discussed about their equations and their solutions. We have discussed 2 types of differential equations today. First is linear SHM differential equation, and another is angular SHM differential equation. Also, we have studied their conditions for the angular oscillations. And at the end, we have discussed about the quantitative analysis of the SHM, in which we have talked about their displacement, acceleration, speed, kinetic energy, and potential energy. We will continue in our next lecture. I hope आपको lectures पसंद आया होगा, समझ में आया होगा. Thank you very much.